My name is Meg Krishnaswamy. This is NLP for All, a workshop series where we look at different important components of natural language processing and work on some real world examples where we can implement the theoretical side of natural language processing. And one of the ways in which I like to understand this workshop is giving everyone an overview of the building blocks that have gotten us to modern language processing technology. And one of the key important breakthroughs that has happened in the last, I want to say last 4 or even 5 years, is speech to text at almost near real time rates. And one of the tools that we had at our disposal, one of the technologies that made this possible is Whisper AI as an example. There are many other speech to text options out there, but many of them work on some very basic theoretical fundamentals that we're going to look at today. Right. So before we start, in case you haven't already, once you're ready with the Google Colab notebook that the links shared in the chat, uh, make sure that your runtime is the T4 GPU runtime, and make sure that before, like while we go through the theoretical fundamentals, if you can click run all, that'll make sure that all of the cells over here are running in the background so that we're ready with the output when we need it. Okay, so right on top, like the little banner that I have is from the paper that Whisper AI, the OpenAI team had published about their work, and it gives us a little overview of how we convert a speech signal with some kind of human linguistic information into text that we can further input into different natural language processing pipelines, right? So we've got tokens. We need our tokens. We need to identify the start and end of our transcript, right? There are all sorts of tags that are added to the signal. Then we might be working on transcription or translation, right? We have to make sure that whatever text is being outputted by the system is time aligned, because we want to know where in the audio signal a certain word or a certain utterance was spoken. And finally, once all of these are done, we're going to we're going to have a text output that could be closed captions, or it could be a transcript, or it could be a subtitle. And I'll go into all of these words. All right. So first, what is speech to text? Now, one of the ways in which we want to understand speech to text for today's workshop is it's a task where we're taking an audio file or a speech recording. We want to make sure it contains some kind of a human speech for the purposes of STT. And what our model is doing is returning the words or sentences or tokens that are spoken. And with this output, we might also get timestamps that help us align the text to the audio, right? Second, this information that's outputted by our system could be called transcripts. A transcript is just simply a file where for an entire for a given audio chunk, which could be an entire conversation or a sentence, we have all of the spoken information saved in a text format, right? Then another popular example is closed captions. For example, on Zoom, if you like me have enabled captions, you'll see that the text is being added to the little box as I speak. So closed captions are just text that's following audio with very little lag, and a closed caption system might include audio descriptions. It might take information from the video and also transcribe it. And most importantly, it's happening as the speaker is speaking, right? Next, we have subtitles. If our closed captions or transcripts are typically being translated from one language to another or one dialect to another, the resultant file is typically called a subtitle file. And one way in which we measure the success of all of our speech to text, or for that matter, NLP tasks, is a word error rate, which is a metric that we typically use to understand how many errors per 100 words in a transcript are being generated by our system. Right now, first up, if you've ever downloaded subtitle files, or if you've ever downloaded transcripts for a given conversation or caption files, you'll notice that the text inside those files is structured in a certain way. And typically, all of this structure is to make sure that a captioning system, while reading all of this text, correctly aligns the text to a given timestamp. And we might also see some speaker information, right? So one of the typical extensions that you might see is .vtt, which is web VTT is very common for displaying time tracks, and it's typically used for HTML5 videos. And if you open a web VTT, like a .vtt file, you'll notice that it'll tell you what kind of file it is right on top. And you'll notice that you'll notice a start time and an end time. So we've got hours, minutes, seconds, milliseconds, and a little arrow to indicate the directionality. This is the end time. So you've got hours, minutes, seconds, milliseconds. And this format is kind of important because in case there are any bugs in how your VTT file is being outputted, it's usually because the timestamp may not be in the right format. Right in the next line, you'll notice that there's the caption. That's what did the speaker say between these two given timestamps. There's a new line, like an empty line, and then the next caption, and so on and so forth. So just in case you've ever generated a transcript file, you see it in a VTT system, this is what it would look like. And if you want to ever manually edit it and you don't want to open some kind of annotation toolkit, you could just use a simple text editor to go over your files. Next, you'll notice that the SRT subtitle format is very similar to the VTT, and the only difference being that the SRT file starts with by telling you what kind of file it is. The extension will be different. Also, each utterance in an SRT file is going to have numbers indicating its position in the list of utterances. So this is just a need to know system. If you're ever working with transcripts, you want to take your transcripts and push them through an NLP pipeline, it's worth it to always know what kind of extension your file has, and what's the information that you might need to remove. And also, it's very easy to convert between all of these formats. So in case you're not happy, or you think your NLP system needs a different format, all you would need is a very simple Python script that can go over all of your systems and give you the format that you need. Next, you might see your transcripts saved in a JSON format. And in this case, all of your information is going to be enclosed in curly braces that are nested together. So if you go over the SRT VTT examples as well as the JSON example, you'll notice some overlap in how the information is saved and some key differences. All right. Again, there are some other formats out there that might be generated by different programs. One of them is like if you use the phonetic transcription and analysis tool PROT, your transcript is going to be saved in the form of a text grid. And so besides the actual content of the speech, it'll give you a lot more detailed information. And again, very easy to convert from a text grid to VTT or SRT. And the bottom line here is transcriptions outputs can have all kinds of formats, but the key information that most of them contain about the speech is mostly the same. And when we are running a natural language processing pipeline, it's a good idea to be familiar with the different formats so that we are able to use them appropriately. All right. So what are some popular use cases for speech to text? Right now, if you've been in Zoom meetings, one of the most valuable things that a transcription service can do for us is improve accessibility. If you're struggling with, for example, the volume control of the speaker, they're not speaking loud enough or their mic's malfunctioning, you turn on the captions and you know what they're saying, right? Another important application would be to create hands-free applications where the input is voice instead of text. And third is because the output of a speech processing STT pipeline is text. It's the linguistic content of a spoken format, where we would be able to take all of that information and use it for downstream natural language processing tasks. And at this point, I'd like you to take a minute to consider what kind of NLP tasks we might want to perform when we get a transcript down. Okay. And while you think about it, I'd like to point out that there are many transcription services available, which all work with a STT, a speech to text model. Some of them are free. So last week I covered Koki and SpeechBrain. Both of these are great applications where they have pre-trained language models that you can use for speech to text across different languages. It does require a little bit of programming, but if you've been part of our workshop, or if you'd like to look at the collab notebooks I shared last week, all of this would be very easy for you to figure out. There are also some paid options out there which have been shown to have great results. The first one, of course, is Zoom, which is free for us. So if you are recording or creating your audio data in a Zoom meeting, generating a captions or transcript file is just one click or two clicks away. Next is the Amazon Web Services. The AWS system has a transcription service as well. But if you've ever dealt with AWS, I caution you, it can get very expensive on your credit card. The third option is Google ASR. Google again has a very professional pipeline that does a speech to text for you and can be implemented into existing code. Again, this is a paid service, and in the case of all of these examples, the actual speech to text processing is happening on the cloud and on their servers. So if your data is private, if your audio data is not something that you'd like to share with any of these big corporations, using a cloud compute system for speech to text may not be the right option. Okay. Having said that, I'd like to quickly look at what Zoom has to offer. So in case we want a complete no-code solution and all you want is the text, since most of us, thanks to our affiliation, should have some form of a premium account, and we would have access to the Zoom cloud, assuming that the audio data that we're talking about is not private. Once our meeting is concluded and you save all of your recorded meetings files, you'll notice that this cluster should have a audio M4A file, as well as a .vtt file. So that's the audio file as well as the caption file. Very easy to access. The other option is if you are looking at the captions, the caption option will have another button that will allow you to access the transcript of the entire talk. And right at the bottom, there is a button that will allow you to simply download everything that was said in a .txt format. So you can do it in the middle of a meeting, you can do it at the end of a meeting. So it's all, as long as you're connected to a meeting and you have premium Zoom access, all of this is one click away. Another thing with Zoom, Zoom offers both translation as well as support for different languages. So as I speak, if you'd like to test it, you can simply change the language settings on the captions and see how well the model performs. So just right now, the captions has been set to English. If you change the language from English to something else, you'll notice that the caption script as well as the text might be completely different. And so again, multiple language support as well as the option uh, to look at automatic captions and save them in a comfortable machine readable format, as well as online almost near synchronous machine translation of what's being said. Right. So in case you haven't tried it, I invite you to give it a try. Like you can open up a Zoom meeting, speak a language that's not English, and see what the transcripts look like as it works through the language detection. I've also added some of the documentation links. So Zoom has pretty well documented notes on how you can access all of these different things. Right. And so there's in case you're collecting some kind of NLP data, and your participants happen to be speaking, this would be a really good and fast option. All right. Now, I'll just pause here for a few minutes and give you a minute to just try out the Zoom functionality or take a look at the documentation. And I will be back in a minute. Okay, so in case you've had a second with to look at what Zoom has to offer, yes, and as I see in the chat, Rev AI and Otter AI are also great examples, and like the fundamentals of how they work are much the same. And I'm just choosing Whisper AI because the functionality is more straightforward, and there are a few other advantages that I will go over as we come to it. All right. So, what are some possible NLP tasks that we could attach to the STT pipeline? First is, of course, conversation summarization. Once a conversation is concluded or we have enough context, we can use the output of a speech-to-text system in order to summarize what was said. Zoom AI is an option. There's a one-click solution here that will generate automatic notes for you as well as summarize the main salient points of a meeting. Next is topic analysis. A speech signal is just a speech signal, but once we're able to extract the linguistic components of it, we can consider what's being said. This includes NLP tasks such as named entity recognition. And finally, we might also want to consider other interesting other features of interest, such as speaker dominance, like in a conversation, who is the person who spoke the most? Maybe there is a way to do it with the speech signal, but doing it with the language data is a better option. And we can also assess the quality of the conversation once we have a language corpus extracted from the speech signal. All right. Next, how did we get here? And this includes almost every modern speech-to-text system. First, as we discussed in one of our previous session, transformers had a pretty big role to play in all of our speech and language models. And we were able to use the theoretical aspects of a transformer-based neural network in order to train our system to better recognize phones, better recognize words, and better recognize utterances, right? And at this point, just a simple distinction between language models and speech models, in case you ever need to consider it. Our language models that we've looked at, this includes Spacey, it includes ChatGPT, Gemini. Their primary focus of as far as data is concerned is written or transcribed text. So they're going from graphemes to linguistic information. They're working to predict the likelihood of a sequence of words And so if you give a word for a given word, what's the next likely word to follow? Next, they generate coherent text based on input prompts. So the input can be anything, but the output typically is some kind of grammatical as well as meaningful text. The training data is usually a large data set containing text. This might contain grammar tags, context tags, semantic tags. And as far as the application goes, we're looking at text completion, machine translation, as well as conversation generation. Right. As now the speech models focus mostly is the processing and comprehension of spoken language. So when we provide an input, which is an audio file, it's going to contain all kinds of energy, and what we're trying to do is process it. So a speech model might work with Mel frequency spectrograms. It's looking at our audio file in the frequency domain. We might be extracting certain acoustic features from it. So that's where MFCCs come in. And once all of this audio signal is processed, a speech model might typically convert it into text in order to look at the language side of things, right? And in case you're curious about what spectrograms are or what MFCCs are, I invite you to look at last week's materials where we covered some of the key terminology involved in speech technology, right? With speech models, they're processing audio for all kinds of tasks. So it's not just language tasks. We might want to do a language or dialect detection where we're just listening to the words, maybe not even accessing a language model and just trying to figure out what this speech signal sounds like. There might be voice activity detection. So if you have a speech signal, what are the time points where someone is speaking and what are the time points where someone is silent? Then there's speaker identification and diarization. So if you have multiple speakers, we might want to know who said what, and separate our stream based on speaker. And it could also be a task like audio source detection, where we want to know if it's a dog barking or if it's a horn or if it's a human speaking, right? Now, once audio processing is done, one of the things that a speech model is doing or may do is identify different linguistic units. So our speech model might be identifying phonemes, it might be identifying words, it might be looking at an entire utterance and figuring out where it started and where it ended, and where another person started speaking and where they stopped. There's also non-speech sound identification, so background noise, animal sounds, bird chirping, and so on and so forth. And our speech models might also be trained to process other nuances of spoken human interaction. So we might be interested in tone, we might be interested in prosody, accent, pronunciation, or in my case, I work with phonetic accommodation and how people start to sound like each other as they keep speaking to each other. And I need a robust and good speech model for my purposes. Right now, with regard to the state of the art models in both domains, we are using transformers at some level, and the objective overall is to predict the next sequence for a given unit. So if I am saying, if I'm making a certain sound, say the sound k, my model is trying to determine what's going to come after k, and it might not reflect in the final output, but as my model is listening to the signal, it's trying to determine what I'm going to say next, right? And a little, this is just a note, and I will say that this is more my opinion. I believe that as far as the context of human speech is concerned, unless we are extremely angry or we stubbed our toe, there is overwhelming evidence that we produce speech, or we use our vocal folds for the purposes of linguistic communication, and amongst other things. And so it might look like speech models are processing something completely different from a language model, but because of the way our tasks are set up, speech and language models tend to work with each other at more than one level. So these are not completely independent things, but there is a great deal of sharing and overlap and tokens and training tasks that make all of these systems come together in order to give us more robust outputs. Right. So in the context of architecture, another major breakthrough was Wave to Wake, which was it was a paper published by Facebook AI in 2020. This is something that introduced a way of training audio without using human annotations. So there are no humans telling the model what's what. You've got a model that's just listening to audio and learning rich representations from it. And this is one of the important this is one of the important developments that got us to where we are, which leads us to web scale supervised pre-training for speech recognition, or Whisper. I found the a full form for Whisper in the footnote of their paper. Seemed interesting. Um, Now, it's basically at some level, the model I would say is called a weakly supervised model, where it's been powered by a great deal of data, which is both labeled and unlabeled. It's from English and from other languages. The captions could be human generated or machine generated in the case of English. The environment could be noisy or quiet. And because of the kind of data that it was given, and because of the model architecture, it was able to perform really well at captioning tasks, no matter what the noise levels are in the background. And at the same time, the training as well as the decoding process both call a lot of tasks at the same time. So the model conducts voice activity detection. It conducts machine translation from target language to English, language identification, and a lot of other subtasks, all at the same time, both at training and testing. And so the output was that Whisper AI was able to run really fast, and the pre-trained model works really well. Another advantage of Whisper AI is that you can basically download a model. You can store a model onto your system, and because you're storing a model to your system, if you have data that you're working on, you're not pinging with a cloud, but you're running everything locally, and that's something that might be worth considering if you're trying to set up your system. Now, my the GPU has disconnected, but I should have my outputs. In case things slow down, I apologize. Right. So first, just a look at the data and pipeline. So we've got 680,000 hours of audio, as well as transcripts. All of this data is from the internet. About 18% is audio that's not from English, but and has English translations. About 17% of the audio is simply from non-English languages, and we've got transcripts from over 98 languages. And because of the kind of data that we have, the model got really good at processing, at identifying speech in a given record. Right. Now, as far as the setup goes, it's a simple. It can happen quite simply on your command line interface. So at the absolute basic level, simplest way to run it would be to simply install Open Whisper and call it and set up your model, and then run it with one line. So I'm going to show some of the potential tasks that we have on our notebook today. The first thing is just very simple and basic speech to text. For this, in this code, I just used wget to download some audio files, right? And the audio files on your Colab should be stored in in your little folder. They will get deleted at the end of the runtime, so just bear that in mind. All right. So next, if you click on the little widgets here, you'll see that two of these audio files are simple sentences. One with relatively low background noise, another one with relatively high background noise. And there's also two songs which I won't play. There's a song in English and a song in Korean. Um, why did I use these files? We'll see. Now, the first thing that we can do is just simple one-click transcription generation, right? And how do we do this? You might need some audio processing tools that I've called here. So one of them is FFmpeg, which essentially converts files from different formats. Whisper might need its own special format. It might need its own sampling rate. And so FFmpeg is something that can process your audio files quickly. Right. So next, if you're interested in the next thing that we want to do is get a model. So that's where load underscore model comes in. There are lots of models, and if you're interested in learning more, the Whisper documentation is a great option. Even for English, Whisper has more than one language model. You might for your task you might need a small model or a medium model or a large model. And depending on how heavy the pre-trained model is that you download, your task efficiency and computational use will be determined by that. Now, as far as creating a simple command to run Whisper is concerned, if you want to know what are the flag options that you have on your command line, you simply run Whisper help, and once you run help, you will get a long text output, which can tell you all the different options that Whisper offers. So yeah, some of these are mandatory. You might need to call a model, and there are defaults that are listed here. I won't be using the defaults. You'll notice you might want to know where you might want to provide your code, the location for your output and input directories. You might want Whisper to actually display every line of output, and that you can do that with verbose. Again, because Whisper is trained and tested on multiple tasks, if your task is transcribe or translate, you can determine that here. Then Whisper automatically detects language. But if you want to save on compute time, it's a good idea to actually tell Whisper which language you're using, be it English. And as you can see, there are no default languages here. So if you do not provide a default language, Whisper is going to take the first 30 seconds of your audio and try to figure out which language is being spoken, which is a considerable amount of compute time, depending on the size of your task. All right. There are a few other options here, which you can, the descriptions are fairly straightforward. Some that you'll see me use is I'm going to use word timestamps in case you want to extract information at the word level, not just at a sentence level. There's also some other options which highlight the words, append punctuation, and so on and so forth. All right. So one thing that in case you're running this on your native system or anywhere else, it would be important to check that you have GPU availability. Whisper by itself takes a lot of time. So in case you're not on a GPU system, things would simply not run. So just make sure that you have to check this, you can run the NVIDIA SMI command, which will tell you what system you're connected to. And if you're able to run the first simple command line one-liner, which I'll explain, in this line, Whisper, I'm giving it a MP3 file. I'm telling it to use the medium-sized model. I'm asking it to transcribe for me. I'm telling it where to save the transcriptions. I'm telling it that I want all possible outputs. So I want a VTT file. I might need an SRT file. I want a text file which has all the text in it and all the other options. And I'm also asking it to give me word level timestamps. Right. So in the command line itself, you'll notice that as Whisper processes your file, it's going to create a little. It's going to display the output of the VTT file or just the transcript. So you've got start time, end time, text. And if your code has run successfully, and you click on the little file icon, you'll notice that a new folder called folder with the name specified has been created. And once you open it, you'll see that there's a JSON file, there's an SRT file, a TSV file, .txt file, and a VTT file. So simultaneously, your text is being generated in all kinds of formats. So if it's a little video that you want to upload to Twitter, SRT is usually the format that Twitter likes. VTT is great for some other options. So accessibility is just one click away. And instead of converting from different formats, you get all the formats in one. And just as an example, if you want to just look at what the different files look like, in this case, once we have all of the entire transcript itself, as you keep scrolling, you'll notice that for each word, the JSON file has a start time and end time, right? So in case your task is more specialized and you want timestamps for each word, that's something that's a flag, just one extra flag that you can use. All right. Now, I want to compare this with a longer English file. And if you run the same whisper command on allstar.mp3, which is a song. So if you're able to listen to the MP3 file, you'll notice that there's a great deal of music accompaniment. There's background noise. There's pauses. It's a lot more chaotic than the simple sentence that we gave it. And even then, our Whisper is able to do a pretty good job extracting the time points where things were said. And as it processes, it will simply give you one line each. And in the same way, if in this case, I gave it a different output file name, and if you look at the files being generated in the output directory, you'll notice that the format of the files is very similar to the previous thing. All right. So this is just simple one-line transcription, right? What else can we do? The other option, other task that Whisper is trained to do is speech translation. And for this example, I'm using a Korean song. I'm telling Whisper that the language is Korean, and I'm telling it to translate for me and save the outputs. And in this case, I'm telling it that the only output format I want is SRT, right? So if you've been able to successfully run it and you look at the output directory, you'll notice that there's just one file there. And I'm happy to just click on this, but you'll notice if you're running it right now that it's going to take some time. It's not, it doesn't happen in real time. It is since the task is a little bit heavier, it might take a little bit longer than the previous file that we ran. Okay, so besides translation, what else can we do? Next, so far we've just looked at command line implementation for Whisper. We give a line of code in our command line, and something is outputted, right? The other option is for us to incorporate Whisper into, say, a pipeline that we're developing. So calling Whisper into Python, making sure that we can add Whisper to a particular specialized way in which we want to manage our data. And for this, there's a little example that I've given here. The source code is available. So if you'd like to see how what was the intention of the original authors, I invite you to check the code source out. Next, here, the first thing that they do is just create a very simple Python function. The function is going to, instead of processing all of the audio, it's going to just take 30 seconds of audio per file that we're feeding it. So this can be a way to make your run very efficient. And in this case, we're simply, instead of while processing with Whisper, we're going to extract the spectrogram itself. So we're going to do the audio processing and save it. And we're going to ask the model to tell us which language it sees. And finally, we're going to ask it to actually do a transcription task, which has been called decode here. Okay. So once this function's been has been defined, if you run the next code block, you'll see that instead of time codes, all we're getting is just the detected language output and just the text, right? So in this case, I wrote this. I mean, this little Python function is only interested in the content of the conversation. We are not interested in start time, end time, and we want to get rid of all of the other information that Whisper provides. So this is a nice way to handle it. Next is we can also utilize Whisper with a web UI. So in case you want to create a little user interface where a person can upload or record a file, and you'd like to create a little system, a tool that we can use is Gradio, which creates a little browser-friendly implementation. And in this example, I've created a little interface that allows me to either upload sound files or record them. And in another box, it provides me with the transcript that it gets by running Whisper on the provided audio. Right. So uh, the way Google Colab is set up, this box may not run very efficiently. So if you're able to run all of the code so far, and you click on the public URL, it will take you to another. Let me see if it works. Right. So it should give you a little web UI like this. If you click on the microphone, it might ask for permissions, and based on how your browser is set up, that's something that that you might need to consider. Now, as I speak, I'm seeing that the browser is recording something. If I click stop, I'm getting some audio, and right away, I've been able to call Whisper AI into my UI, and I'm seeing instant transcripts. So again, some of the factors over here could be the mic quality and background noise, but for the most part, Whisper is fairly robust. I speak with an Indian English accent, so sometimes I don't get perfect results, but it's a pretty good model when the audio quality and other factors align. All right. Next, once we're able to get all of our information, if you're running a Whisper at scale, one of the things that would be very important is to make sure that the output you get is of a quality that you can work with. And in order to assess output quality for an entire data set, one of the calculations we can use is word error rate. And it's fairly straightforward. Python has a package for calculating word error rate. All we need to do is provide the data in the right format. And so in the next demonstration, we're going to call the Jiver package that's going to do the word error rate calculation for us. And we're going to use all of the things that we've used so far for setting up Whisper, with one important difference. In this example, instead of just running it on one small little file, I'm going to call an entire data set. And in this case, it's the Libri speech data set, which has recordings with human-generated transcripts. And what I'm going to do is I'm going to ask Whisper to generate transcripts for every audio file in the data set. And for every audio file in the data set, I'm going to compare the human-generated transcripts, or the gold transcripts, with the output that Whisper has generated. So we want to see how different our automatically generated transcripts are from the original transcripts. So if we have one file, it's fairly easy. We can do a little count. But when we have lots of files, we need something more sophisticated, and that's what we're using in this example. Now, I'm not going to run the code here because it is quite time consuming, and it might these functions in particular take longer because it's an entire data set. All I'm doing here is setting up my code, setting up all the libraries that I will need. Once my libraries are set up, I'm trying to see if I have GPU access. Very important when we use Whisper AI. The next thing is there's a little class here that's going to call my data and process it. It's going to take the audio. It's going to take the entire data set. It's going to convert it into a format that can be used in a task like this. It's going to find out how many items are there in the data set. And finally, it's going to take the audio, it's going to take the sample rate information and text, and it's going to run Whisper and extract the log-mel spectrogram that we're going to use later. What is a log-mel spectrogram? It's just a nicely processed audio signal in the frequency domain, which we can input into Whisper in order to work with it. So instead of giving our entire pipeline the raw audio text, I'm going to carry out a little pre-processing step just so things are more efficient. Right. Next, I'm just setting up the language audio model. And if you've been able to set this up and you look at the text that's being printed out, it's telling you that we've called an English-only model because LibriSpeech happens to be an English-only data set. So I don't need to call a multilingual model over here. And it tells me how many parameters that we have. And again, you can always change this if you're evaluating a data set that's in Korean or Japanese or Hindi. All we have to do is set up a different language model. You can tell the model what you want, and once you have your model and your data set up, all we need to do is the next step. Right. So the next thing is that I'm using is a little for loop. And what the for loop is doing is it's going through the entire data set. Every time it encounters a sound file, it's going to run the sound file through our language model and get a transcript. So we have for every sound file in the data set, we come up with a automatically generated transcript. And we're going to create a little data frame where the automatically generated transcripts and the gold transcripts are aligned next to each other. And if you were able to run the next two boxes, you'll notice the data frame. And one of the ways it's very important, the way they look different. The generated transcript is all capitalized, but only in a grammatical way, while the gold transcripts are all caps. And that's just something that was done to make sure that researchers could distinguish between them. Now, because Jiver, the word error calculation, the calculator that we're using is going to be very sensitive to these differences, we want to normalize our output. And so in the next code block, we're just going to use a normalizer function. And all the normalizer is going to do is make sure that all the special characters are removed and make sure that all the capitalizations are removed. And this will make sure that the text on both sides is identical, just so that it does not interfere with our word error calculation. All right. So now once we have our data in a usable format, duly normalized, all we have to do is run the word error rate calculator. You can call it with jiver.wer. You tell it what is the expected outcome. And so that's the gold transcripts clean. And then you give it the items that we are evaluating, which is the generated transcripts in this case, right? And once you print the actual output is not going to be it's not going to be the number of floats in the actual WER output are quite high. And so all we're doing is, because we want our word error rate in a percentage format, I'm simply pretty printing it to get a word error rate, which is 4.28. And to interpret this, for every 100 words that our system encounters, it seems to get about 4 or 5 wrong. Now, another thing that we can do here is, because we can carry out the word error rate or a word a calculation at a file level. and we can identify what are the different files where Whisper is having trouble. And that's something that will help us automate the process of cleaning up our utterances. Another thing, based on your task, 4.28% word error rate might be very acceptable. Um, or if your task is, again, this is for English, if you ran the same, I invite you to run this for other languages and see what the word error rate calculation is. It could be 50% or 40% and 30%. And that is one of the ways in which we can run inference for a given speech model. And if you are using Whisper, this is something that you can also make sure to automatically understand what your output is like, instead of manually reading and going over thousands of lines of text, right? So that's all I have for you today. Most of these are demonstrations. Given the kind of scale at which the model operates, I did not run all of the code in real time. But I hope that you are able to run the code and get the kind of results that I'm getting. Every time you call an instance of the model, you might notice small differences in the word error rate. I got 4.28 here, and when I ran it on another GPU, I got 4.27. It happens every now and then. There's a lot of randomization and random seeds that create those differences, but the numbers shouldn't be too dramatically different. Yeah, and I hope that this overview on speech to text is something that's useful. And if you'd like some more support on running your own models, or if you'd like to know a little bit more about how these things work, I'm more than happy to answer your questions. And this concludes our workshop series, NLP for All. If you have feedback for me, if you'd like more topics to be covered, if there are more things that you think would be of general interest, please don't hesitate to email me. I will add my email in the chat. And thank you so much for joining. And I hope you have a great weekend ahead.